Welcome back to the second installment of these review sessions for 6034 Fall 2020. Last time in the previous review session, we talked about, it was a review session for models of problem solving, in particular search. So we're presenting a problem in the form of a search tree or search diagram and then solving that problem with the appropriate search methods. And this recitation is going to be, or not recitation, this review session is going to be covering the fourth and fifth recitations, which were rule-based systems first, and then Bayes nets. So this is a review session on models of inference. Rule-based systems being inference under inferring in when there is no uncertainty, and then Bayesian inference being reasoning or inference under uncertainty. So I'll just jump right into it. Full disclosure, I'll be recording this review session in parts, so it's mostly much in the spirit of the previous review session. I'll be solving the quiz in real time, but I'll cut it in the middle in order to ensure that the recording is as smooth as possible, so that you have a better viewing experience, or so to speak. So on to part one. So as previously, I trust that if you are viewing this video, you are perfectly capable of reading on your own, so feel free to pause the video here so that you can read at least this first part of the prompt, and then I'll jump into the question right afterward. Okay? So we're treated with the following forward chaining assumptions. You don't have to necessarily familiarize yourself with them right now. I'll project them next to the iPad screen once I'm working on the question by showing the tear-off sheets. So this is a pretty standard rule-based systems question, perform forward chaining on this set of rules and assertions that we have. So let me bring up the wrong one. There, the rules and assertions, and now I can just jump straight into solving this. So the first rule that we have is, or that I see matching, is P0, and it matches to the assertion 0, and so far that's all we have. So to start writing, P0, and P0 is the one that fired, with X being bound to dad. I'm gonna abbreviate it to the first letter, either a D for dad or B for Boris, because I'm a bit constrained for space here. And that produces assertion 3, that, dad says to ask Boris. Okay. And now let's try again for round 2. Now I get a match for both P0 and P1. If you're wondering, I should highlight. So here I've highlighted Boris, and if you look on the left on the rules, the consequent of P0 says X says to ask Y, and we only have an X binding, X equals dad, for sorry, X equals dad for P0, but I omitted to say, look at the fourth assumption in the forward chaining assumptions on the left hand side. I believe my mouse, yeah. So here, consider the variables to bind in alphabetical order. So what I did is P0 bound, or P0 fired here, and X is bound to D. I have another variable that needs to be bound, Y, for the consequent to be complete. So I just went in alphabetical order, and in reality I'll actually delete it from here and rewrite it so that it's much more explicit. P0, here I have X equal to D, Y equal to B. just because I went in alphabetical order as the fourth assumption on the left-hand side says. So now I have P0 and P1, and P0 fires again, but this time it's going to be because x equals d. That one is bound off the bat because the assertion 0, the one that matches, is that says to you ask dad for permission to use the car. Sorry. And then the remaining variable to be bound following the alphabetical order is d as well for y. So assertion 4 becomes dad says to ask dad. I'll just highlight it to highlight that I was going through alphabetical order for through the variables in alphabetical order for P0. And just as a reminder, because we don't have any delete clauses in the rules, now that P0 and P1 are matching, they are going to continue matching until the algorithm stops running. So now I have P0, P1, and let me think, has P0 gone through all the possible variable combinations such that it doesn't produce any new assertions? And yes, because x is fixed so far, and it's gone through the only two possible y's that it could take, dad and Boris. So now P1 must be the one to fire. And assuming it does fire, sorry, it matched, assuming it does fire, let's see, Boris is, sorry, let me start by reading P1. A says to ask B, which means that matches with assertion 3 and assertion 4. We're going in order, so assertion 3, which means the bindings this time are A equals dad, B equals Boris. If I read that correctly. Yes. Which means assertion 5 becomes you ask Boris for permission to use a car. I'll leave it in 3 dots because that's not going to fit with my handwriting. You ask Boris for permission to use the car. And now we go again. P0 and P1 are still matching because, again, we don't have any delete statements. And let's see, there is P1 can fire again because this time we can match it, instead of to assertion 3, we can match it to assertion 4, which means A6, after binding A to D, to dad, and B to, oh, whoops, I bound those incorrectly actually. Let me backtrack a little bit. You asked Boris for permission to use the car. Sorry, I misread. You asked Boris for permission to use the car. I should have written it, in hindsight, I should have written it completely A5. That's what I think messed up my reading. Now I have a match with P0 again, but I have not a match. Now P0 can fire once again with a new variable binding, P0. And this is the new variable binding that can take place. X equals Boris and Y equals Boris. If we're following Y doesn't need to be bound to anything, so we're going through alphabetical order. Or when I say it doesn't need to be bound to anything, it's not bound in the antecedent, therefore in the consequent we're going in alphabetical order through the possible bindings of Y. So this is X equals B, Y equals B. Then assertion 6 becomes Boris says to ask dad. And I'll highlight the 2 because this is what's novel in this situation. Now P0, P1, and we were going in alphabetical order, which means the other new assertion that can be produced by continuing the alphabetical order is, let me keep the tally to make sure mistakes like the previous one don't happen again. So this is x equals Boris, y equals dad. Boris says to ask, oops, I mixed up the steps. In the previous one, it was Boris says to ask Boris, alphabetical order, and then Boris says to ask dad. I swear it's the pressure of solving problems in front of a camera. Okay, so assertion 6, Boris says to ask Boris. If the first time assertion 5 matches with P0, and then the second time, because we're going in alphabetical order for y, for the second variable that needs to be bound, Boris says to ask dad. So we have the two possible matches, or the two possible new assertions, and now let's do another round. P0 and P1 still match. And then does anything match, or do any new assertions happen? And we know we've exhausted all the possible new assertions in P0 because I've already written assertions with all possible combinations of variables: dad, dad, Boris, dad, dad, Boris, Boris, and Boris. Only 4 combinations of those variables. In the case of P1, let's see, do we have anything new? We already have the assertion for you ask dad for permission to use the car, and we already have you ask Boris for permission to use the car. So in reality, there are no new assertions that can be produced by P1. So this is none, no rules fire, no new assertions. So this algorithm ends. It comes to a close. And the follow-up question to this is, will you get permission to use the car? Well, these rules went in a cycle about asking the other person or the other party. So we did not, at the end of the day, get permission to use the car. And why or why not? And this was asking for a simple explanation. There were 3 possible explanations one could give, such that you would receive full credit or actually genuinely answer the question. The first one is the obvious one, that the rules are cyclic. And what that means, and I won't write them down, but I'll say them to the camera such that you know, and they should be, this should be explained at least on the paper, is that the rules cause a cycle where the matched rule will lead back to itself. And you saw that you saw it very explicitly just now. I was going in circles with the assertions were matching to the rules that produced them, and if not, to the other one, and so back and forth. So I think the rules are cyclic is the most obvious one, and the point has been most proven there. And the one that caters more toward the nature of forward propagation, or not forward propagation, forward chaining, is that the forward chaining algorithm finished, but the hypothesis, abbreviated H, was not found in the remaining assertions, or in the new assertions. Abbreviated A. So all the possible new all possible assertions were produced given the original assertions and the rules, and we never found one that says you got permission to use the car. And then this one would be a more observational one, which would be that the hypothesis doesn't exist as a consequence of any of the rules. So this would be I say a more observational one because you could literally point your finger at the rules and say none of these rules are a template that says X or Y gets permission to use the car. And because that's never a template and it's not in the original assertions, then how could it ever be produced? So that's that for asking for permission to use the car. And the other standard type of question that one gets with rule-based systems is backward chaining. As usual, I won't pause. Feel free to pause the video here, read the prompt, and digest the questions. I'll have these rules in the left side panel. Oh, there they are. Yeah, there it's more or less well aligned. So the rules will be there. You're free to read the prompt at your leisure. I'll jump in. So we have another base set of assumptions. Again, feel free to read at your leisure. And we want to prove the hypothesis Villanelle is not a psychopath, which is a very positive theme for tonight, but it is what it is. Fair, I have nothing against the question, I just wanted to make the comment. Oh, sorry, I accidentally bumped the mic. Okay, so let's say this is the first hypothesis or the first assertion that I check. Villanelle is not a psychopath. H1, it's redacted there. I'll be zooming back and forth through both pages because as I draw the tree, I'll be updating my list of hypotheses that I've checked. Okay, so Villanelle's not a psychopath. It matches with, with P0. Thankfully, that's an OR node, so we start off easy, and we have that on the left one, or the first child, is that X feels bad after tricking Z. We know that X is bound to Villanelle. I won't start the trend. I'll abbreviate it as V because it'll become a lot of text. And actually, I'll separate these a little bit. Not the prettiest tree you've seen. Definitely not the ugliest one I've drawn. Okay, so Villanelle feels bad after tricking Z. Next we have Villanelle had an unhappy childhood. And then V is in love with Y. Okay, so the next one to check is V feels bad after tricking Z. And you may ask, why haven't I bound Z yet? Well, there is no assertion in my list of assertions yet that would match to any binding that I would give to Z. So I essentially am skipping that step. If I were to bind Z to Villanelle or to Eve, which are the two possible variables here, I would essentially just backtrack. And it would be a needless backtrack, so I'm just dropping it and skipping it entirely. So P0, and then the other reason that I'm skipping it is this this node matches with the consequent x feels bad after checking y. So I can expand here P2. So V is in love with Y. V tricks Y. And V is a professional assassin. And these are all contained in an AND node. And so here comes an important concept that I briefly touched upon in the rule-based systems recitation in the matrix example. So we have V is in love with Y, and I could go ahead and bind Y to something if... Actually, I wouldn't bind Y to something because there's no assertion that would satisfy it. I would just match it with P3 and continue expanding, so on and so forth. But I also have to recognize this one, V tricks Y. There are no consequence that match and no assertions that match V tricks Y, which means whatever matches here wouldn't really matter because this is an AND node and the middle child I already know is not going to match to anything. So in reality, I'm short-circuiting here. I'm going to short-circuit this node and this node with the middle child. And I want you to remember that we did something similar to this with an OR node in the NEO example in the matrix in recitation 4. And the difference is, in that case it was with an OR node, in this case it's with an AND node. And the implementational detail that I want to bring about is it's very conceivable that you would check out of all the children or child nodes of this rule, if it's an AND node, are there any that outright do not match anything? If there are, just break and don't bother checking or expanding the rest of the children, because we know that this is not going to be satisfied in the case of an AND node. In the case of an OR node, you could check in the children, are there any that match an assertion, which means they're true and don't need to be expanded. And if there are, then you can just break and confirm that that node is confirmed because it's an OR node and one of its elements was true. So we know this was true, or not true, this is false. And let me update the above hypothesis with what I've just done. So what am I missing? Oh, I'm missing just number 3, V tricks Y. And because I'm backing out of, this was P0, or because I'm backing out of P2, I forgot to write it here, I'm no longer, I've seen that P2 doesn't yield true, and I'm backing out of it and going to the next child in P0, then this is backtracking. Okay, and now I'm going to check number 4. V had an unhappy childhood. Okay, and what does this match? this matches P1. And what comes is V's mom was mean. This is going to be number 5. Then after V's mom was mean, the match that I have is two children with, and it's an OR node with P4. So V wasn't allowed to eat ice cream. And V was sent to boarding school. Okay, so I'm just going to go ahead. I'm going to be checking 6, and I see that it doesn't match any consequence of any rules, and it doesn't seem to match any assertions. So this one is out of the question. And the same thing happens with V was sent to boarding school. It doesn't match any consequence nor assertions. So this is false. And now, yet again, I'm going to backtrack. Well, let me update the list of hypotheses that I've checked, and then I'll talk about backtracking. This is a lot of text, so I'll just abbreviate this to no ice cream and boarding school. So we were relatively flexible when people said this is backtracking, going from no ice cream to boarding school. In reality, I don't consider it backtracking, because remember that these two are children of the same rule, P2, or not P2, sorry, P4. These are two children of P4. So in reality, you're not going up to another node, you're just changing children within the same node. It depends on how you look at it and implementational details. In the way I'm treating this problem, going from no ice cream to boarding school isn't backtracking, but then when the boarding school rule does not match any consequence or assertions, we're moving away from P4 and we're going back up to, in this case, P0, to the next child of P0, because we've disproved at least this middle child. So definitely failing the boarding school rule, or not matching the boarding school rule, and going to V is in love with the Y, which is the rightmost child here, that is definitely backtracking. So speaking of, let's test V is in love with Y. There aren't any assertions that would match this, so I'm not going to bind Y yet. But what it does match is rule P3. And now I get V tries to poison Y. And I'm going to check this one. But now I'm going to check variable bindings, now that because two things. this doesn't match any consequence that I have. V tries to poison Y. But, so the fact that it doesn't match consequence should immediately prompt me to try to assign some binding to Y to see whether it matches the assertions, which you could consider it some last-ditch effort to see whether it works. So I'm going to say Y equals Eve. And I'm going to scan through my assertions. And in fact, I see that A1 matches. So this, after binding Y to Eve, V tries to poison Eve. This matches, which means the hypothesis is satisfied or is proven, because this is an OR node at the very top. So we've proven the rightmost child and we've satisfied the hypothesis. There is a way, so I talked about this backtracking, which was actually very new to a lot of students at the time. We decided if one doesn't recognize the backtracking here, then it's possible to get to the same result just by filling out this tree. So continuing this line of thought. And I would encourage you to try this on your own and try it with and without the, not the backtracking, sorry, with and without the short circuit. And I think it would be good practice. Okay, and this is now following the backward chaining. We get a conceptual question. It's meant to be, I'm going to say, relatively easy because you've just completed backward chaining, which takes a lot of brain power, as well as forward chaining. And thankfully, my brain is going to appreciate at least this question. What is the difference between forward and backward chaining in general? And this is there's a very key difference here, or there are multiple key differences that I want to highlight. Forward checking, you generate new assertions from existing assertions and rules, until you can't anymore. Pardon the handwriting. So let me talk about, or write down, backward chaining, and then I'll discuss the difference a little bit more in depth. So backward chaining builds a goal tree from hypothesis, or hypothesis if you're trying to prove one hypothesis, to consequence, antecedents, and assertions, but I'm just going to say consequence and assertions. But it's not that backward chaining builds a goal tree, it's that it builds a goal tree in order to prove or check the truth value of the hypothesis. Check the truth value of a hypothesis. So this is what one of the key differences. Forward chaining is not goal driven. Forward chaining will produce new assertions until no more assertions can be produced, and if you were looking for a particular assertion, you can search through the list of assertions after the fact. But forward chaining will not actively look for the assertion. In backward chaining, it's the opposite. Backward chaining actually doesn't produce any assertions. So you don't in a way, the list of assertions when you do backward chaining is off limits. You can't touch that, or you can't modify it in any way. But in backward chaining, it is goal driven because the goal is exclusively to prove or to check whether a particular hypothesis is true or not. And so once you've proven whether the hypothesis is true or whether it's false, then you stop whatever execution you're doing because the goal has been fulfilled. So that's the major difference. So now we'll have some rule logic manipulation exercises. Again, I'll pause here, or feel free to pause here, read it at your own leisure. I'll update the the side panel so that we all have, oh, that's for the next question, so that we have this on hand. Let's see, I just want to zoom in a little bit. I believe that's good enough. Okay. I trust that you've read the prompt, and we're asked here to combine and simplify the two rules P0, P1 into one rule called P2. And the way I start thinking about this is this not raises a red flag immediately. And the reason it does is because not what it does is if a particular pattern doesn't match any assertions, if in the case of an antecedent trying to match two assertions, if a pattern doesn't match, then it yields false, and then not will turn it into true. So what not is it's saying this pattern was not found. So if the pattern X wins the popular vote is not in the list of assertions, then not is going to say that that's true. X wins the popular vote is missing. That's what not is saying, or that's how I interpret not. And then X loses the popular vote if it's not explicitly stated. And then we have in P1, let me erase, actually I'll leave those annotations up there. We have or X wins the popular vote, X loses the popular vote, and then outside of the or, one of those has to be true, and then along with X wins the electoral college. So if I'm interpreting this correctly, because either of these can be true or both, and this one is the consequent of P0. Actually, let me reorient that. Yeah, the arrowhead should be there. So this is the consequent of P0, and P0 is only looking for the fact that when X wins the popular vote is not in the list of assertions, then P0 really isn't contributing much to P1 in a way. Because when you think about it, if X wins the popular vote matches something in the list of assertions, then the or condition in P1 is going to be fulfilled, and whether X wins a popular vote or whether X wins the electoral college, that's a separate issue. If X wins the popular vote is not in the list of assertions, then P0 would add the X loses the popular vote, and the or would be there. But the true determining factor in whether X wins the election, as in the consequent of P1, is whether X wins the electoral college. And I'm not thinking U.S. politics. I'm thinking electoral system. I'm thinking through the possible scenarios in which the or at the very beginning would affect the outcome. So I'm going to condense it in the following way. If X wins the electoral college, then X wins the election. And in reality, logically, that is what P1 is saying. X can win the popular vote or lose the popular vote. It doesn't seem to matter as long as that pattern is in the list of assertions. The important one is X wins the electoral college, then X wins the election. So if another way to look at it is if X wins the popular vote is not in the list of assertions, then P0 would yield the consequent or the assertion X loses the popular vote, and then the OR condition would be true anyway. So whether the desired assertion is in the list of assertions or not about some comment about winning the popular vote, it doesn't really matter because P0 would handle it. So P0, if we eliminate this OR and P0, then we've essentially condensed P0 and P1 into P2. Moving on. Whoops. That was unintentional, my bad. I'll stop. Please feel free to pause here and digest the information. I'll go straight into answering the question. I won't talk too much about logical consistency because it's explained here on the test itself. So we're given the hypothesis X wins the election, and we're asked for both rule set P01 and P2, which set of assertions out of these four make H of 0 true. So P2 should make it easy because let's go back to P2. If X wins the electoral college, X wins the election. And we're trying to prove X wins the election, or produce the hypothesis X wins the election. So we need two sets of assertions that would match with, in the case of P2, X wins the electoral college, such that we produce X wins the election. And in that case, it would be S2 and S3, because A1 would match with Bush wins the electoral college, and then Bush wins the election according to P2, and Obama wins the electoral college again in P2. Obama wins the election. And then you can try for yourself with these, with S2 and S3, how P01, the P0 and P1 would react to this. So my answer is going to be S2 and S3. So which sets of assertions make not H0 true? And what that means is it's not that they would produce the assertion X loses the election, is that they would fail to produce X wins the election. That's the kicker. And in that case, it's S0 and S1, because even though they have Gore loses the electoral college, Perot loses the electoral college, they do not match with either P2 or P0 or P1. Well, in reality, they match with P0, but P1 wouldn't be satisfied because of the AND here. So the hypothesis Gore wins the election or Perot wins the election would never be produced, which would mean that not X or not H0 would be true. More generally, given a set of rules, an hypothesis, is it possible to have a set of, so this is a more commentary, this question, on the not that I've been addressing since the start of these questions. So essentially, is it asking, is it possible to have a set of assertions that will produce J0 and not J0. And I'm not going to bother writing it down. As I've said before, not says this pattern is not in the list of assertions. But a value of true as in disregarding not, a value of true means that pattern was matched in the list of assertions. So it's impossible because not H0 is true if H0 doesn't exist in the assertions. H0 is true if H0 exists in the assertions, so they can't really happen at the same time. So now we're asked, and this I was checking it in my head, but I've forgotten that we do explicitly do some amount of forward chaining on the rule sets that we produced. So I'm going to pick as the set 2. So this would be Bush did not win the popular vote. Bush wins the Electoral College. And I'm going to apply it to P01 first. And we have P01 on the left-hand panel, or on the left-hand panel, the screen is flipped in my case. Let's see, and I've already forgotten the rule. Bush did not win the popular vote. That means that not X wins the popular vote is matched, and let me just start writing before I forget what I'm saying. P0 with X equal to, that's going to take up too much space. X is equal to Bush. And then I get the following assertion. Bush loses the popular vote. Then I get P0 and P1 matching because now the OR inside the inside of P1, sorry, the OR inside of P1 is matched, and that also matches or makes the outer AND match. So now P1 can fire with X equal to B again, and I get A3. Bush wins the election. And both P0 and P1 can match again, but in reality nothing fires because there's nothing new to add to the list of assertions, and therefore new assertions is none. Okay, so forward chaining. Iteration 1, let's see. Matched is, I'm forgetting, I need to go back and check. Let's see, Bush did not win the popular vote. Bush wins the Electoral College, and my rule is about winning the Electoral College, which means P2 matches. X equals Bush. And the assertion produced is Bush wins the election. Let me scroll up quickly to my P2 such that you can see, and also for my own sanity to check. Okay, so this is, yes, this is in fact the rule that it does match with Bush wins the Electoral College, therefore Bush wins the election. It's only one rule and only one variable, which means yes, P2 did match, but there's nothing new to fire and no new assertions therefore. Okay, so this question is asking whether P01 and P2 are logically consistent. So instead of writing it, I'm just going to talk aloud. Yes, given the same set of assertions, P0 and P1 did reach the same truth about H0, about X winning the election. And the new assertions are irrelevant in this case because we were only interested in the hypothesis. So whether we had the assertion Bush loses the popular vote, that's irrelevant to our logical consistency test because we were just checking that a particular hypothesis was proven. Okay, so we have now the one final rules problem, and it's about writing our own rules. Again, I'll stop so that you can read at your own leisure. I'll grab a drink of water while you do so, and feel free to resume the video when you're ready. Okay. So we are asked to write a rule, in this case for Michael Scott, in which he is essentially asked or ordered for all of the pretzel toppings, or if Michael Scott has all the pretzel toppings, then he is happy. And I think that's a fairly straightforward thing to do. If you want a heart attack, that is. So I'm going to abbreviate because it's a lot of text. Pretzel, I'll write the first one, is topped with mustard, M, and then same thing, except it's topped with cinnamon sugar, same thing, topped with cotton candy, same thing, topped with chocolate sauce. So if all of those are true, all those toppings are true, then Michael Scott is happy. So as a reminder, we're asked to, I should have said this in the prelude, we're asked to write rules that represent these situations. So we're not dealing with variables per se, we're already binding the variables to describe particular situations. And we've just described the situation of the big boss, who seems to be large and in charge, at least in this question. Now we're doing it for Creed, and this one will be complicated because, let's see, only one topping can be true, but not both, and it's only two of them. So this one might be a little bit more complicated. So I'm going to use variables, and you can then change, as in I'll say X is equal to topped with mustard, and then Y is equal to topped with cinnamon sugar. So now that I've defined those variables, I'm just going to use them to keep it clean. So if we have both X and Y, that's bad. We don't want Creed to have both at the same time, which means it's good if I only have one, if I don't have both. So what I'm saying here is that both topped with mustard and topped with chocolate sauce are not in the list of assertions at the same time. So either of them could be there because either of them can be there if the other one isn't, because then the and would be false and not would make it true, saying they are both not they are not both in the data set in the list of assertions. So that part is covered. So it's in that regard, we're saying either this is saying either one or neither. So I need something that would convey the second part. At least one of them has to be in the set. So let's start with an or, because in reality it really is either topped with mustard or topped with chocolate sauce. Now let me stare at it a little bit more. So at the top I'm saying they should not both be there. At the bottom I'm saying either one or two of them, because or is obviously true if either X or Y or both are true. But if both of these are true, this is going to be false. Sorry, if X and Y are true, not is going to be false. If X and Y, if one of these is true, this is going to be true. If X is false, Y is true, this is also going to be true. Which would mean I want both of them to be true. Both of these I want to be true. So I'm going to make this an AND. So if AND, that should be the last statement, or if this AND that contains a not and another embedded AND and then an or at the bottom, then Creed is happy. There is another way of solving it, and I think it would be worthy practice for you to test out what is an alternate way of writing this. The solution that I arrived to, it's not the only one. If you write a valid alternate solution, of course you would get full credit. This is just how the solution to which I arrived using my own logic, and hopefully how I approach these problems and how I do them has helped you so far. In the next part of the video, which again I will be recording separately, I'll be talking about Bayes nets and Bayesian inference, or solving through the Bayesian inference component of this exam. Okay, so I'm back after a short break, and now I'll jump straight into the Bayesian inference part of this quiz. So now we're moving away from reasoning under certainty and then reasoning under uncertain. In certain situations and then reasoning under uncertainty. Let's see. Whoops. As usual, feel free to pause here, read at your leisure. There's a lot of information to digest. I trust that you've paused, and as long as you need it, and I'll just jump straight into the question without much preamble. So this first question is a fairly standard one to ask. Calculate the number of parameters that you would need in a joint probability table, making no assumptions about independence. And because I can't make any assumptions about independence, let me just write out the formula that would give me such a value: number of parameters Again, reminder that this is under no assumption of independence, and I'm taking the product for each of the variables I. So each variable in the probability tables, all n of them, in this case 5 or 6, I'll talk more about that briefly. And what I want is the number of values in I, so number of possible values that it can take minus 1. Okay, so let's look. Now I want to address the point, is n equal to 5 or 6 in this question? So is it this or is it this? And I want to draw a probability table in order to highlight it. So let's say that I have two variables, a and b. This is unrelated to the top. And I want to calculate the probability of some event happening given a and b, or the probability of, let's say, yes, some event happening given a and b. So this is the probability of c given a and b. So a is true, b is true, a is true, b is false. Whoops. False, true, false, false. So how many parameters do I need in this probability table? So I would need P1, because in the universe where A is true and B is true, C can be true with a probability P1 and C can be false with a probability P1 minus P1 using the exhaustion principle. Same logic applies to all the other combinations. If this is unfamiliar to you, please visit recitation number 5, I believe, is where I talk about the basics of probability. P3, 1 minus P1 plus P2 plus P3. So if I were asked how many parameters do you need, and I know technically there are 3 variables, but I'm using two of them to predict the third one, or to help me predict the third one. So the possible values of C isn't really, well, to some extent it's playing a role, but it's not, I'm not factoring them in this calculation, because in reality the constraining factor is A and B. Because there are 4 possible combinations, it's 2 times 2 minus 1. And it certainly helps that C can either be true or false, as can A, but that's precisely what I'm getting at here. So I'll leave this up actually. I'll leave this up and just keep it there as a thought. So now because I'm predicting A, I have some long probability table with a bunch of values and combinations of, what is it, DMLCW? And then I want the probability of A given everything. Then it's eventually going to turn into P1, and then that's enough because A is true or false, it can be 1 minus P1, and then P2, 1 minus P2, etc., etc. So I'm not going to consider A in the calculation, I'm just going to consider all of these independent variables. Or when I say independent, it's because I'm using them to predict A, not that they're independent. Reminder, I'm not making any independence assumption by using this formula. Okay, so I have that D has 2 values, 2 possible values. This is the product of everything. So then W has 4 possible values, L has 2 possible values, then C has 3, W has 2. And then all of that minus 1, and that is equal to 2 times 4 is 8, times 2 is 16, 48, 96 minus 1 is 95. If only my hand would agree with my mouth. 95. Okay. That's the number of parameters. And now the follow-up is use the Bayes net assumption and calculate the new number of parameters. So here it's relatively similar logic to what I was doing earlier. So I'll start with the top level because there are no extra parameters influencing the possible probability of D or C. So what values did D or C have? Or the range? It was 2 and then C had 3. So let's think about C first. So C has 3 possible values. I know they can be less than, equal to 3, or greater than 3. I'm just going to express them as X, Y, and Z. So the probability of C equaling something, or C equaling X in this case, would be P1. C equaling Y would be P2. C equaling Z would be P3. But because this is a probability distribution, and according to the axioms of probability, all of this has to sum to 1, and because these are all the possible values of C, then this must be 1 minus P1 plus P2. So C, by virtue of having three possible values and no parents that influence its probability table, then it only needs 2 parameters. Then the third one is just 1 minus the sum of the other 2. And D, fortunately, has just 2 values. So it would be, in the case of D, the probability table would be P1 and then 1 minus P1. This is 2 minus 1, basically. Okay, let's see. Who else now? I'm going to go with M, because M has no parents either. And by the same logic, there are 4 possible values for M. The fourth value could be 1 minus the sum of the other 3. So this is 4 minus 1 equal to 3. Now let's talk about L a little bit. In the case of L, the probability of L being true, so let's say this L equals true. They don't necessarily, actually let me check how many values L can take. So L can be either true or false, thankfully. D is either weekday or weekend. Because it's only 2 values, I'm going to say D can either be true or false in this case. It doesn't affect the answer, it just makes it simpler to write, given D. So this is D, this is true, this is false. So the probability that L is true, given that D is true, is P1. And then the probability that L is false, given D is true, is 1 minus P1. And then the same applies to when D is false, because that's a different universe. Then I have a different set of exhaustion parameters, which means this is 2 because I have 2 parameters from D, and then 2 minus 1. That's the case of L. I have 2. And then the same logic applies to W, actually, because it would be the same, except this would be X, Y, Z, and then W would take, how many possible values is it, true or false? So it would be P1, P2, P3, because there are 3 different universes. C equals X, C equals Y, C equals Z. So this is 3 times 2 minus 1. That's equal to 3. Then comes the big one. Let me make a little bit of space over here. Okay. So if we're thinking about A, when we were talking about, or when I mentioned the number of parameters and I was going through, okay, so this is a possible universe, that's P1, this is a possible universe, that's P2. So when I add variables, the combinations of values of those different variables are different universes, and each universe is going to require its own set of parameters. Because thankfully A is either true or false, I only need 1 parameter per universe, because let's say my parameter for universe 1 is P1, and that's for A equals true, then A equals false is just 1 minus P1. So I just need to count the number of universes, or in other words, the number of possible combinations of values in the three parents of A. And by doing so, I'm applying the Bayes net assumption. I'm assuming A is independent of D and C because its three parents are given. So there are actually there are two possible values in L because it can be either true or false, and M can take on, what could L take? I forget. Yes, true or false. M could take 4 different values, and then W could take 2 values as well, which means, and then A is true or false, so 2 values minus 1, and that's going to be equal to 16. And now here at the bottom it just says what is the total number of parameters, and this is just reading them. Sorry, that's embarrassing. That's this is just reading them off. So it would be 1 plus 2 plus 2, that's 5, plus 3, that's 8, 11, 27. Okay, and this is another fairly standard question. This is, you're given a formula or some potential expansion of the chain rule, and the question is this the most efficient way of writing this expression? If not, show that it can be simplified more. And I'm just going to go ahead and provide the simplest form of this expression. And the way I'm going to do so, actually, I see that we'll need to keep track of the variables, so there. That way we can see where the parents are and which is which. Okay, so I'm going to say this is P of ... that mess. I don't want to have to write it more than once, or more than, I don't want to have to write it. The trick with these chain rule expansions in Bayes nets is to start in reverse topological order. So you start from the bottom and then you go up, and typically I go up by levels, and I'll show you what I mean. So this is a probability of A given C, D, L, M, W times the probability of L given C, D, M, and W. And because I'm going up by levels now, I wouldn't go up to D, I would go sideways to M. The probability of M given everything else, C, D, W, times the probability of W given C and D, times the probability of D given C, times the probability of C. And now I'm just going to take my red pen and start eliminating in variables that are conditionally independent of each other. So let's start with A. The Bayes net assumption says that A is independent of its non-descendants given its parents. D and C are non-dependents, so I can eliminate those. And I can continue with, let's see, I can eliminate, in the case of L, its parent is given, so M, W, and C can be eliminated. In the case of M, it has, technically its parents are none, so if I have a none given, I'm just going to say because its parents are none, it's conditionally independent of those, and you can prove it via D separation. So if is M independent of C given nothing, is M independent of D given nothing, is M independent of W given nothing. The probability of W given C is therefore independent of D, which has nothing to do with it, and then D and C they don't have parents and are not connected directly in any capacity, so that they're independent of each other, and that is more or less the final expression. Let me just write it out in clean. Probability of A given LM W, probability of L given D, probability of M, probability of W given C, times the probability of D, and the probability of C. And this is Bayes-Net assumption in full force. There are other possible orderings that would yield similarly efficient expressions. This is just one of them. This is my favorite because it's fairly methodical in how I expand the chain rule. Let's see. This is just a copy of the Bayes-Net. And now I'm being asked, can this expression be described with fewer terms, A given W and C? And the first thing that I can point out is W is the parent of A and C is the parent of W, which means A given W is conditionally independent of C. But one would have to, so it's true. And the way to simplify it would be by doing this. The way to show it would be by performing D-separation. Or this is the Bayes-Net assumption basics, but I think a good way of showing it and good practice is to do D-separation. So is A conditionally independent of C given W? So first, I need to draw the ancestral graph. D C M L W A. Oops, I skipped a step. Then it's to link the parents. D C L M W A, and then I make the graph undirected. I've basically already done that, so I've skipped a step. Step number 4 is to delete givens and their edges. Let's see, W disappears because that's my given A, and then I read off and I see that there's no connection between C and A, which means A and C are structurally independent, or they're conditionally independent given W. So that is true. And now yet another one is W given A equal to W given A and L. Let's see where L is. I keep scrolling up, but I forget I have the graph right on my face. So L is right there. And before giving the answer, let's just do some more D-separation practice. So I want to know whether W is independent of L given A. Because if they're conditionally independent, then the above would be true. If W and L are conditionally independent. Let's see. Ancestral graph. And this is the ancestral graph of the variables in question, not the givens. Which is why I'm not going to write This one will be missing. Now I have to link the parents. I'm just going to make the graph undirected as well while I'm at it. Now I delete the givens and their edges. In this case, the given is A, so I end up with D, L, W, C, and there is a path from W to L right here, which means they are not conditionally independent. Whoops, given A. So this is actually not true. Structurally speaking, we're assuming that the numbers will also work out because it's rare. But yes, structurally they are not independent, given A. So yet another one, actually no, this is not a t-separation one. This is explaining away. So this one was a little bit contentious, and the reason it was is if you remember, if you're new to probability and you saw the explanation of explaining away in recitation 5, then you would assume that this is, and you understood it correctly, then the logic that would go into this is, let's say given that your friend attends a movie night, there's likely a reason that explains it, and if your friend has a lot of work, then your friend is less likely to attend a movie night due to just because that your friend has a lot of work. But if your friend has a lot of work and still attends, then there's a higher likelihood that it's because of something else, such as the movie being held on a weekend instead of during the week. So this work helps explain why, or work would explain why the weekend, not explain because we're calculating the probability of the weekend, and this is why explaining away is hard to explain, ironically, it's more likely during the weekend if there are more factors against it going on, such as your friends having work. But this is a discussion that borders on the line of out of scope of 6034, because we start encountering noisy or versus noisy and terminology. Because the concept of explaining away is that one event that is unlikely explains away the need for a second event, but the opposite is also, so that's a noisy or, but the opposite could also true, which is the noisy and what determines one or the other is the likelihood of the events on which we are conditioning. So if it's I won't comment on this setup. If it's very likely that your friends attend and that that they have a lot of work, so they usually have a lot of work, but they usually also attend, then it's a different setup than if it's rare that they attend and it's also rare that they have work. So those are different setups. You're not required to know that because it's out of the scope of 6034. It's only to understand the basics of explaining away and in the way that we do so. And I won't go deeper into this example because it's only meant to be a refresher. So I suggest, if you found that a little bit confusing, I recognize myself that I haven't done the best justice to this concept because it's difficult to explain. I recommend you go to recitation 5, where I do go into it in more detail using an example. And if this noisy or versus noisy and business is very confusing and intimidating, don't worry about it. Okay. So let's change in pace and go to the second part, movie critics. And I'm going to update the graph here, and we'll be working with probability tables later on, but actually I'll just keep it to the top graph until I actually need the information at the bottom. So now we have fewer variables, and as usual, just pause the video, read at your own leisure. I'll just continue. So we are asked first to list the variables that are structurally independent of K based on the BayesNet. And I keep scrolling up and down, forgetting I have it right on my computer screen. Structurally independent of K based on the BayesNet. So let's apply the BayesNet assumption then. And I'll just write it out explicitly. K is independent, that's too long, of its non-descendants given its parents. K has no parents, so it's completely independent the way it is set up right now of R and I, which are non-descendants of K. I guess I should have just written this here. But another way of proving it is with d-separation. And if you're looking for more practice, I recommend that you perform d-separation with the following: K independent of I and K independent of R, given nothing. So I can just say this, given nothing. And just try to prove my statement when I answered R and I are structurally independent of K. And now this is something that I hinted at lightly in another question: what is the difference between structural and numerical independence? And I won't write it because it involves a lot of words and it's easier to speak them. So structural independence is what we observe in these Bayes-nets when we perform d-separation and there's no connection between variables. There, the structure of the Bayes-net is such that if they are structurally independent, they are numerically independent. So let's actually write that. Structural independence implies numerical independence. And the problem is it doesn't go the other way around. So there are cases, so it's not a constant. There are cases, for example, when you perform d-separation and there is a path from the two variables of interest, then you would say, yes, these variables are structurally dependent. Yet there are cases where even though that happens, when you work out the numbers for numerical independence, which is defined as for two variables a and b, the probability of A given B is equal to the probability of A. So that's the definition of numerical independence. It may be the case that two variables that failed in d-separation still have the numbers work out in such a way that this is still true. So lack of structural independence does not necessarily mean that two variables are not numerically independent. It's rare that they disagree, but it's not constant. But on the flip side, if two variables are structurally independent, then they will be numerically independent as well. That's the end of my long-winded commentary on this. Okay, so now we actually are going into the, feel free to pause the video and read while I update the graph on the left-hand side, or left-hand side, right-hand side. The fun fact, the webcam is flipped because the extra pane is on the left-hand side, even though it's on my left, but when I look at the webcam view, I'm looking toward my right. It really throws me off sometimes. Okay, let's see. Let me get this set up. Okay, so now I'm ready. What is the probability that a movie has a stellar cast P of S? Okay, so let's see. What information do I have about S? So S is not one of the, S has a parent, which complicates things, but not very much. And that's about it regarding S. So it's fairly standard. The probability of S, and if this equation is unfamiliar to you, I recommend that you go back to recitation 5, take a look. So I need the probability that S is true, and I have the probability table S given K. But what I'm missing is the probability that K is true. So the way I would write this is the probability of S given K, and now via the chain rule, the probability of the probability of K plus the probability of K being false. I'll write it as, or sorry, I'm flipping the order. Probability of S given that K is false, that's in the probability table, times the probability that K is false. And you might be asking, where the heck did this equation come from? So remember that this is the probability of S and K being true, plus the probability of S being true and K being false. And that is none other than the exhaustion principle. So I'm summing all the universes where K is true and S is true, and the universe where S is true but K is false. And that would give me the total of the space where, or the total universe where S is true. Okay, so now I just plug in numbers. The S given K is on the probability table, 0.9. Then what is this? Oh, 0.01. Plus 0.6. And then this would be 1 minus 0.01, so that's 0.99. And I'll admit that I'm cheating. I have the number written down in front of me. I was not about to calculate that in my head. So this is 0.603 for Teehee. Okay. So now this is another calculation, and we'll probably be using the exhaustion principle and some combination of the chain rule, or some combination of the exhaustion principle with the chain rule to solve it as well. Let's see, we are asked to just recompute using a newer value for P of K. And what does that mean? That means I'm just going to rewrite the equation from above. So this is equal to 0.9 because the other probability table hasn't changed, but this time it's 0.2 plus 0.6 and it was 1 minus 0.01, now it's 1 minus 0.2, and that should be 0.8. And that is equal to 0.66. Okay, moving on. Fairly standard stuff. What is the probability that the movie is good? So P of G being true given all this other stuff. So I think the first thing to do is look at the Bayesnet and think, what do I need from all the information that I'm given? So I have I, S, and K. I, S, and K, and I believe it would be a worthy exercise for you to verify, is G conditionally independent of K given S? And I know I mentioned this earlier for a different problem. I'm forgetting which letters it was, and by Bayesian assumption that should be true, but I recommend, this is a good place to practice your d-separation skills in order to verify. But I'm going to say that G given I, S, and K is equal to P of G given I and then S. Reminder, try this exercise with d-separation so that you confirm with your own eyes, pen and paper, that K is really conditionally independent of G when given S in particular. So it's important that you give S, and I think it should be clear when you delete givens, when you get to the step of deleting givens and their edges, because then you delete any connection between G and K. I've basically given you the answer at this point, so I may as well write it. It's G, is G conditionally independent of K given S? Moving on. Sometimes I can't help it. Let's see. What next? So I have G given I and S, and when I look at my table here on the right or on the left, depending on which perspective you adopt, I see that I have I have S, but I don't have R. But I can apply the exhaustion principle. So I know that this is equal to P of G given I and I, S, and R times probability of R plus the probability of G given I, S, and not R times the probability of not R. And this is the same logic, and the same logic of using the exhaustion principle and the chain rule together that I did in the top, in which exercise was it? It was, oh sorry, it was question 6.3. Same logic, it's just a little bit, there's a little bit, it's a little bit more involved, but same principles apply. And I believe I have everything here. So the concept being, notice in the table that I have two cases where both I and S are true. So so if you can see my mouse, here I and S are true and R is false. And where again are they both true? At the top, I and S are true, and R is also true. So I'm summing this this one with this one, but because of the chain rule, I'm also multiplying it by the probability of R. So this is the top row, 0.95, times the probability of R, that's 0.8, plus the lost again, F false true true, that's 0.8, times 1 minus 0.8, that should be 0.2. And I'll cheat again and use a number I wrote down beforehand. This is 0.92. And I believe this is actually, yes, this is the end of, that's the end of this quiz, of the base section at least. So I hope this was useful. This was a good refresher. In the best case scenario, I've at least, or in the worst case scenario, I hope I've reminded you of certain topics that you need to review in preparation for the final exam. And in the coming videos, I'll be reviewing the remaining topics of the course using the other two quizzes. So until next time, I'll see you then.